Good morning. Welcome to this short series on complex variables. Last time we started looking at specific problems in contour integration. We will continue that, but before we do that we need a few theorems. Okay, we need a few theorems which we will merely state and accept. Okay. So they are as follows. Let f of z be given by n of z by d of z be a rational function such that the degree of dz exceeds the degree of nz by at least 2. Then limit r tending to infinity integral over a circular arc CR f of z dz equal to 0. Okay, we have already used this idea. Now we will refer to this as the degree of polynomial theorem. Okay, whenever we need it, we will call it the degree of polynomial. Okay, degree of polynomial theorem. Next, we will need another very important theorem. It is called Jordan lemma. Okay. What does it say? Suppose on a circular arc CR, on a circular arc CR, the complex function f of z tends to 0 uniformly as r tends to infinity, then limit r tending to infinity integral over the circular arc f of z, which is uniformly tending to 0, e to the power I k z dz equal to 0. And it is important that k be positive. Okay, so we will refer to this as the Jordan lemma. Okay, this will be used several times in the problems to come. Okay. Next, very often we will be moving around a point z0 using an arc which has a very small radius epsilon. Okay, we exaggerate this. There is a point z0 and we will move around the point z0 using a small circular arc. The arc radius will be epsilon. Okay, so we will call this the C epsilon arc. Okay, so theorem number 3 says, suppose on a contour C epsilon z minus z0 f of z goes to 0 uniformly as epsilon tends to 0. Epsilon tends to 0. Then limit epsilon tending to 0 integral over C epsilon f of z dz is equal to 0. Okay. We will call this the C epsilon theorem 1. When we use it next, number 4, related to the same figure. Suppose f of z has a simple pole at z equal to z0 with a residue equal to C minus 1. Then limit epsilon tending to 0 integral C epsilon f of z dz is equal to I times phi times C minus 1, where phi is the angle subtended by the arc. And is taken positive positive in the anti-clockwise sense. These are some theorems that we will be using. Okay. So now let us continue with our examples on contour integration. Okay. This was probably example 3. Okay. We started looking at a very interesting example, which is integral minus infinity to infinity sine of ax by x dx with a positive, and the idea we had proposed was that if we look at this integral minus infinity to infinity e to the power of iax over x dx, that can be written as integral minus infinity to infinity cos ax over x dx plus integral minus infinity to infinity, I comes here, sine ax over x dx. So we will deal with this integral as though our objective is this integral, and when we get the answer we will take the imaginary part. That is the idea. Okay. Now as we have said before, if this is what I call, now this is what I call I. Okay. I is my starting integral without this imaginary. So I formulate now an integral on a closed contour C, and I now change the variable I a z by z dz. The contour I choose is this. The original integral goes from minus infinity to plus infinity. Okay. But here, as long as it was sine ax over x, x equal to 0 was not a problem, because this is a sinc function and it has finite limits as we approach x equal to 0. But in this form, e to the power iax over x or e to the power iaz over z, this is a complex plane now. At z equal to 0, this function blows up. So now the contour we choose is we come from minus infinity on the real axis. At minus epsilon, we choose a small circular arc, we circumvent the singularity, then we proceed towards plus infinity and close it with a circular arc. So this is portion 1, this is portion 2, this is portion 3, this is portion 4. Okay. if the integral you want passes through a singularity, then you have to evaluate it gently by taking a small circular arc of radius epsilon and then sending epsilon to 0. There is no choice of completely avoiding the singularity, but we will evaluate what happens as we pass through it gently, and that is done by initially taking a small contour of radius epsilon along the singularity and then sending epsilon to 0 as a limiting process. Okay. So now we have 1, 2, 3, 4 portions. So my j I write as integral. I can write it as minus r to minus epsilon, okay, e to the power of I a z by z dz plus integral, okay, over c epsilon contour e to the power of I a z by z dz plus integral, again going from epsilon to r e to the power of I a z over z dz plus integral over c r e to the power of I a z by z dz. In future I will shorten this way of writing it because we have just started. I am giving you the full form. Now I have not left space to put limits here. Limit epsilon goes to 0 and r goes to infinity, okay. Here epsilon goes to 0. Here again limit epsilon goes to 0, limit r goes to infinity, and here limit r goes to infinity. Okay. So these are now, as we have seen earlier, in the sense of Cauchy principal value. Okay. Now this first portion or first leg and third portion together will give me the integral minus infinity to infinity e to the power I a z by z dz. But I have the two portions. I have the second portion or second leg and a fourth portion, fourth leg. Now let us look at the fourth leg, okay, fourth portion. We have said in the Jordan lemma that if I have a function f of z, okay, on a circular arc, okay, that goes to 0 uniformly as the arc radius goes to infinity, my f of z in this case is 1 over z. So 1 over z goes to infinity as r goes to infinity, because I will write z as r e to the power of I theta. And so now my integral f of z, which is 1 over z e to the power of I a z dz equal to 0 as limit r tends to infinity. This is Jordan lemma where a is positive. So fourth portion follows Jordan lemma and it goes to 0. Okay. Now we have the third portion. The third portion is this integral over c epsilon e to the power of I a z by z dz. Okay. Here the c epsilon second theorem comes into play. We have a function which is e to the power I a z by z, which has a simple pole, at z equal to 0. Okay. Hence this integral is equal to I times the angle of the arc phi times the residue at that point. Okay. So that angle is pi. Okay, the phi value is pi because we are going through a full half circle, but we are also going in the clockwise direction. So I have minus pi, okay, and c minus 1 is the residue. So residue for this is what? E to the power of I a z divided by z into z evaluated at z equal to 0, which is equal to 1. So that is 1. So this whole value is minus I pi. Okay. So where do we stand? We started with j, which is equal to the closed contour integral on this c e to the power of I a z by z dz. Okay, that is equal to now the integral I want, which is minus infinity to infinity e to the power I a z by z dz. Okay, this is coming from first and third portions. Then the c epsilon gave me minus I pi and CR gave me 0. Now that is equal to what? If you noticed, our contour does not include any singularity, and therefore there is no residue contribution from any pole inside C. So this is going to be equal to 0. Okay. So now what do I have? I have integral minus infinity to infinity. Now this z is on the x axis, so z equal to x. So e to the power I a x by x. This is moving on the real axis. This part is moving on the real axis, so therefore z is x. Dx is equal to I pi. Okay, and I said the portion we want is the imaginary part of this. So we take the imaginary part of this and we get pi. So integral minus infinity to infinity sine ax over x dx equal to pi. We will do the same problem now, but this time in the contour we will include the pole. Okay. So students often have this immediate doubt as to, by avoiding the pole within the contour we got this answer. Do we have the same answer if we include the pole? Yes. Okay. So we will look at that problem. Okay. So the problem is the same. Integral minus infinity to infinity sine ax over x dx. Okay. But this time we will include the pole in the contour. So how does the contour now look like? So, this is a complex plane. I will come from here. Okay. Singularity is over here. So, I am moving on the real axis. Okay. I am showing it above because the path will not be clear. So, now we go below. We move forward and close the arc with CR. So, this is portion 1, this is portion 2, this is portion 3, this is portion 4. Okay. So, this is CR, this is C epsilon. Okay. Now, the singularity is inside the contour. Why? Because we will start again with J is equal to closed contour C e to the power of I a z over z dz. This is singular at z equal to 0. Okay. So, we will do this now very quickly. The first and third portions give me what I want. So, I will write it minus infinity to infinity e to the power I a x by x dx. Okay. And then we have the C epsilon portion plus integral C epsilon portion e to the power of I a z by z dz. Then the CR goes to 0 here also using Jordan lemma. So, we won't include that. However, now we have included the pole. The pole is inside. Okay. So, I will get a residue from that twice pi I times the residue at z equal to 0 of e to the power I a z by z. Okay. Now, we are moving in the counterclockwise direction. So, I will get twice pi I and the residue here is 1. Okay. The residue here is 1. Why? Because e to the power of I a z by let us say z minus 0 multiply by z minus 0 and evaluated at z equal to 0. So, that is equal to 1. So, I get twice pi I. Okay. Now, here again the second C epsilon theorem holds. Okay. So, z is a simple pole and we are going around a C epsilon contour. Okay. So, what happens is I get I times phi. Phi is the angle covered, which is pi, okay, times the residue. Residue is 1. However, this time I am moving in the counterclockwise direction. So, the sign is plus. So, I get I pi from here and I have 2 pi I on the other side. So, what I get now is integral minus infinity to infinity e to the power of I a x over x dx is equal to, I will shift this I pi to the other side, twice pi I minus I pi, which is equal to I pi. Okay. Again, if we take the imaginary of this side, I get pi, which is integral minus infinity to infinity sine ax over x dx. We will do the same problem using 2 more methods, and one of them will include the method of deformation of the path. Okay. So, let us look at that. The next method of doing the same problem is this. So, the problem is same, the third problem, integral minus infinity to infinity sine ax over x dx. So, let me just make a statement, and the time is running out. So, we will stop and continue. So, this is exactly equal, an identity equal to e to the power of I a x minus e to the power of minus I a x by twice I x dx, and we will write this as integral minus infinity to infinity e to the power of I a z minus e to the power of minus I a z by twice I z dz. Okay. This is exactly equal to this on the real axis. So, we will continue with this problem in the next lecture. Thank you.